All right. So when you write a chemical reaction, you have the reactants on one side, you have the products on the other side, and you use an yield arrow because you may not get exactly what happens. Now, sometimes it's, a huge percentage. Like in this case, you can expect, approximately 99-ish% of the time you should see sodium chloride. But there's many reactions where 2 or 3 different types of things can happen when you mix these things together. Like, for instance, iron and oxygen. Iron and oxygen mixed together, the vast majority of the time will do iron 3 oxide, but it can also do iron 2 oxide. And then there is some weird, there's like super oxide irons that are very, very odd. So anyway, but this is the vast majority of what happens. But again, we use a yield arrow because it's not equal. It's not 100% of the time. So when it comes to writing a reaction, say for instance, we have hydrogen reacting with oxygen. Well, hydrogen and oxygen are diatomic molecules, so that means they exist as H2 and O2. But when they react together, they will produce water. And the problem we have with this is that there appears to be a hydrogen here and a hydrogen here, and it's bonded to, it's going to react with this oxygen. But when we go over here, well, there's the hydrogens, and there's the oxygen. So where'd this guy go? Seems to have just disappeared. And according to the law of conservation of mass, you can't destroy matter in a chemical reaction. So where did this guy go? And how do we write that so that when we are writing a chemical equation, it works out? And the answer is we use coefficients. We write numbers here in the front that multiply everything throughout to show how this reaction is going to occur in the number of things that are going to need to mix together to show an actual conservation of mass. So in this case, in the case of our water and our oxygen, these two hydrogens hang out with this oxygen to form our water molecule. Well, that means then that this oxygen is going to need to go somewhere, which means it's going to need another hydrogen molecule over here so that it can become a water. So what you see then is that this reaction will take place when 2 hydrogens react with 1 oxygen to produce 2 waters. It's very much like cooking. You take 2 cups of flour and 1 cup of sugar and, a bunch of different numbers of ingredients to produce, like 24 cookies or what have you. So we use these big numbers in the front of a chemical reaction to denote how many of those particular molecules or atoms are needed for the reaction to be what we call balanced. And we call it balanced because it's basically just like a teeter-totter where you have the fulcrum in the middle and so the yield arrow is our fulcrum, and we need to make sure that the number of reactants or the number of atoms that are on the reactant side are the same number of atoms that are on the product side, because we got to account for every single one of the atoms. So drawing a picture like this is one way to balance chemical reactions, but that makes it very tedious to do. What we're going to do is we're going to go through some tips on how to balance chemical reactions quickly. And let me show you that. Nope, 4 different units for live versus online. There we go. This is my in-class work stuff. All right, so here we have a bunch of chemical reactions, and what we're going to do is we're going to look at the first 10 of these guys here. What are you doing? Why'd you close? I don't know why this thing closes these things. It drives me nuts. All right. Ooh, I can move that later. Okay, go away. All right. So let's take a look at these chemical reactions, and we'll balance them. And I'll give you some tips on how to balance chemical reactions quickly and easily without having to use that method where you're drawing the pictures. So the first tip to balancing chemical reactions is to start with the largest element, or the largest thing, we'll just say. So when you're starting off, we're going to skip number 1 for now. When you're starting off with something like number 2 here, we could do iron, we could do oxygen, but this thing has the most stuff in it. It's the largest of the elements, so you can see it's one of those other weird iron-oxygen compounds. So if we started with the iron first, or if we started with the oxygen first, that's going to affect this more than if we started with this first, because whatever we do to this is going to translate into what's going to happen to the other ones. So if you are starting off with the thing that has the most stuff in it, then you're probably starting off with affecting the whole thing, and you can just kind of make little changes to what's going on here. So tip number 2 is to deal with the biggest thing, or sorry, tip number 1 is to deal with the biggest thing first. Tip number 2 is to leave elements, so things that are all by themselves, for last. So we're going to go over here, we're going to look, and we're going to be tempted to mess with this iron and throw a 2 here, okay? But if we do that, that won't actually fix all the problems. So what we're going to do is we're going to look at this and go, okay, here's iron. Iron needs to be fixed, but so does oxygen. And if we're going to leave iron by itself for last, because it's just by itself, we can do whatever we want to it, then this is suggesting that we should fix the oxygens first. So let's do that. Let's put a 2 here to fix the oxygens. And remember, these coefficients affect everything. So there are now 4 irons over here, and there are 2 oxygens. Well, that makes this balance. But now, since we followed tip number 2, that means that we can now fix our iron with a 4. And for the 95% of the time, you want to make sure that your balanced numbers cannot be reduced anymore. So if you have 8, 2, 4, well, that should be reduced to 4, 1, 2. All right, so that's our first and our second tip. If you do that, then you can balance these ones pretty easily. So here's a tip for number 3, which is going to be our third tip. And that is what I call attack the odd. So when it comes to making the numbers the same on both sides, when you have an odd number on one side and an even number on the other side, odd numbers are harder to deal with when it comes to multiplication than even numbers, because even numbers all share their ability to be divided by 2 in common, whereas in odd numbers are all over the place in what their different dividers are. So the best bet, if you're trying to make something the same on both sides, is to, what I say, attack the odd. And how do we make the attack the odd? We make it even. And how do you make any odd number even? You multiply it by 2. So if we follow our rules, or sorry, our tips, we're going to start over here with this because it has the most junk in it. We're going to ignore aluminum for now because rule number 2 says we should leave elements alone till the end. And then tip number 3 says if you have an even on one side and an odd on another, you should counteractively attack the odd thing rather than the even. So how do we make an odd thing even? We simply double it. Now we have 2 aluminums and we have 6 bromines. 2 had a hard time becoming 3, but it doesn't have a hard time becoming 6 because 2 times 3 is 6. And so if 2 times 3 is 6, then 3 times 2 is 6. And then we just simply go over here and put a 2. And so that's what I mean by attack the odd thing. If we didn't do that, then we would be like, oh, let me fix this, and we'd go back and forth, or maybe you'd fix this thing and then have to go back and it would bounce back and forth. So this kind of helps you just kind of do this, do this, do this, and then move on. All right, so the 4th tip is what I call polyatomics. So treat polyatomics like X and Y. What do I mean by that? Well, if you see this reaction up here, this is nitrate. But you'll notice over here, the nitrate didn't break up into nitrogen and oxygen. It stayed nitrate. So rather than balancing out those N's and those O's individually, why don't we just treat this thing like X? So this is AgX, and this is HX. And then you'll notice right here, we have sulfate. Well, sulfate didn't break up. It stayed sulfate. We can treat this like Y. So rather than balancing S and O, we can shorten all of our work here by simply just balancing out these things, nitrate like a whole thing, nitrate, and sulfate like a whole thing, sulfate. So let's go ahead and balance it now, but using our techniques. Tip 1 says to start with the biggest thing. These guys are kind of the same size, so we start with either one. I'm going to start with the silver sulfate. And tip number 2 says leave elements till the end. There aren't any elements. Tip number 3 is attack the odd. Don't really see that right now. And then we are actively doing tip number 4. So first things first, it says silver is a 2. So we're going to put a 2 here. That balances out our silvers. But now I have 2 X's, or 2 nitrates. So I'm going to go over here and I have 2 X's. So I also have 2 nitrates. This gives me 2 hydrogens, which is exactly what I have. So that right there is tip number 4 in action, where we can leave things balanced on both sides. So this guy right here, number 4, is a good example of all of our tips put together so far. We have our nitrate on both sides, so we can do tip number 4 here. We have our big ugly mess, and we also, we don't have an odd thing, so we don't have to worry about that. But we can also leave our silvers and our coppers till the end. This one's actually pretty easy to balance if we follow our tips. We come over here, we start over here. We worry about the copper and the silver last, where you don't have to worry about odd things. So we're going to go down to this, and we're just going to balance up our nitrates. There are 2 nitrates here. There's only 1 nitrate there, so we're going to put a 2. And then tip number 2 said, okay, now we can start worrying about copper and silver. Well, we don't have to do anything to copper, so all we need is a 2 there to balance the silver. Pretty simple. This one here is a great example of tip number 3, because we're going to leave aluminum alone. We're going to start over here with the aluminum oxide. We're going to leave aluminum alone because it's an element, so that's the last thing we should worry about. So our first thing to deal with is our oxygens. And so this is odd, that's even. So we should double it. And that gives us 6. So we should triple this. It gives us 6. And now we have 2 times 2. That's 4. And finally, for our 5th tip, we have diatomic molecules. Diatomic molecules can be cut in half. So, why do I say that? Well, if we look at this reaction here and we follow our tips, or up until number 4, there aren't any polyatomics, so we don't have to worry about that. Not many odd things, so we don't have to worry about that. So really all we have is just start with the biggest thing with the most stuff in it. So we start over here and we say, okay, well, there's 3 carbons, so we're going to write a 3 here. And there's 6 hydrogens, so we're going to write a 3 here. So that balances our carbon and our hydrogens. But now, to balance our oxygens, I've got 3 times 2 equals 6 oxygens here, and 3 times 1, which equals 3 oxygens there. So if we add these together, that gives us 9 oxygens. So what number times, some number times 2 equals 9? Well, that number is 4.5, but is it okay to do that? And the answer is, for diatomics, yes. And the reason why is this is oxygen. So if you cut oxygen in half, it's still just oxygen. And this is hydrogen. So if you cut hydrogen in half, it's hydrogen. But this is water. And so if you say you have half a molecule of water, how does that work? It doesn't. So the only molecules that you can cut in half are diatomics. Now, if you're like me and you don't like the 0.5s, then what you can also do is you can just double everything. So instead of this being 1, 4.533, you could also make this 2, 9, 6, 6. You'll notice that both of those are very simple ratios that can't be simplified any further. And that's balancing. Pretty simple stuff. You guys probably all remember that from 8th grade. You have a lot more examples in your classwork. I just like using this one. It's just a bunch of examples on top of each other. Now, you may also run into word equations where they write out the words and they want you to write a chemical reaction and then do it. So like, say for instance, it says aluminum plus oxygen, and then it'll say yields, aluminum oxide. There's not 2 L's in aluminum. It's one of those mornings. Oxide. So to do this, you'll have to write out the actual formulas of everything. So aluminum is Al, and then oxygen. Now, if you just write O, you're going to get it wrong because oxygen's one of what I call the 7 diatomic molecules. And then aluminum oxide, well, that's a name, so you'll have to write that formula using the techniques we learned last unit, which will give us that. So oxygen is actually a diatomic molecule. So if you want to know what are the diatomic molecules, there's only 7 of them. You can write it on your periodic table if you want. Hydrogen is an element that exists as H2. Then it just basically goes across the period. Then we have nitrogen, then we have oxygen, and then we have fluorine. These guys are diatomics as well. Carbon is not, boron is not. Then we basically just go down the periodic table. So then we have chlorine, and then we have bromine, and then we have iodine. These are the 7 diatomic molecules. So if you're if you're looking at a word equation and they ask you to balance it, write it and balance it, and it says oxygen or hydrogen gas or nitrogen gas or whatever, you need to make sure you write that 2 there. And if you're ever having a hard time balancing a chemical equation, it's probably because one of the formulas wasn't written correctly. Because otherwise they should fit together pretty quickly. So you can write these 7 diatomic molecules down, or on your periodic table, if you've printed that out, you can just put little 2s next to them. A lot of teachers like to say Hunkelbrief. They write it like this. So that you can go Hunkelbrief, but I don't like Hunkelbrief. I don't know. It doesn't sound like a name to me, but maybe it does to you. I like the 7 at 7, because if you look at the periodic table, there are 7 diatomic molecules that start at nitrogen, which is number 7, and they make a 7, because it goes oxygen, fluorine, chlorine, bromine, and iodine. So it's the 7 at 7, and then hydrogen. But either way, however you like to remember it. So that's balancing chemical equations. Pretty simple. All right. So now, if we're talking about chemical reactions, we want to talk about different types of chemical reactions. Now, when it comes to actual real-life chemistry, they're going to break chemical reactions into inorganic and organic. But we don't do any organic in high school, so we're going to ignore that. And so rather than just talk about all reactions being organic, really it just breaks down into what's called redox reactions and some other types. But basically everything boils down into redox reactions. But we're going to classify this a little bit further. And we're going to do the 5 types. I'm going to say 5 basic types of reactions. Okay. So there are 5 basic types of reactions, and they all have names, but really what's happening here is we're oxidizing or reducing or we're changing the charge of something, and that's what we call redox reactions. So we're going to say that there are 5 basic types of reactions, and if you know these 5 basic types, you can use that information to predict the products or the reactants of something that has occurred. So they kind of break down into 3 categories, 2 that are kind of similar to each other, another 2 that are kind of similar to each other, and then 1 that is probably your favorite type of reaction out of all of them. So what are the 5 types? Well, let's just start off with the easiest one, and that's the one that's probably your favorite, combustion. Combustion is the simplest to remember because it always does the same thing. You're going to need some sort of hydrocarbon. So a hydrocarbon is any carbon-hydrogen molecule that has a certain amount of carbon, a certain amount of hydrogen. You can have other things inside of the carbon-hydrogen molecule, like oxygen, nitrogen, but as long as you have C and H, then what can happen is that molecule can react with oxygen. And when it does this, it will produce every single time carbon dioxide and water. So these are combustion reactions. If you've ever played with a Bunsen burner at your school, or if you've ever turned on your stove in your house and you have a gas stove, then what you have done is the combustion of methane. Methane is the gas that we call natural gas. Natural gas also has some ethane and propane in it, but it's a very small amount. Most natural gas is like 90 to 95% methane. And it will react with oxygen to produce CO2 and water. Every single combustion reaction does this. So you've probably heard your car runs on gasoline, and sometimes you've heard of what's called octane rating. So octane is C8H18. And so that will react with oxygen, and you guessed it, produce CO2 and water. That's what's nice about combustion reactions. They're the easiest to predict what will happen because they always do the same thing. Now, there's also what's called incomplete combustion, where you can produce carbon monoxide, but for the most part, you guys don't need to know about that for the test. It might show up in your book, but you can ignore it. And of course, these are fun to balance because sometimes you'll need to do that half an oxygen trick. For this one, you don't need, for the methane one, you don't need to do that because it's very simple to balance. You just simply put a 2 there, which gives us a 2 there. Very easy. But for this one, the octane reaction, we will need to put an 8 here, and we'll need to put a 9 there, which is going to give us 16 and 9, which is what? 25. So this will be a 12.5. Or you could simply go 2, 25, 16, 18. So either way. So these are combustion reactions, very simple reactions to predict. All right, so let's talk about the ones that are pretty similar to each other. Let's talk about synthesis and decomposition. So synthesis means to make, and decomposition means to unmake. So in a synthesis reaction, we have some sort of elements or 2 compounds, and what they do is they come together to make one product. So you have the dead giveaway that you have a synthesis reaction is that you're only going to have one product. On the opposite side of things, a decomposition reaction only has one reactant. Because in synthesis reaction, we're going to fuse 2 things together, and a decomposition reaction, we're going to split them apart. So a great example of this is what looks like the combustion of oxygen, but is really the synthesis of water. Because what we have here is we have 2 elements, and they are coming together to make one product, water. If we go over here, we can have the decomposition of water, where we take the water and we split it up. This is called electrolysis. So this is really easy. You can take some hydrogen gas and you can just put flame on it and it will burn and it will produce water. But if you want water to split back up into hydrogen and oxygen, you're going to need to pass a bunch of electricity through it, and then you can split them up. A great example of another decomposition reaction that you guys have all probably dealt with is hydrogen peroxide. That brown bottle you spray on your boo-boos and it starts to sting and bubble up. Well, what's causing that is that this is decomposing into water and oxygen gas. But in this case, the oxygen is liquid, and it's dissolved up in the water, and it's very violent and will react with just about anything, which means it's going to kill any bacteria, which is good, or viruses is going to pop them, which is good. However, it's also going to kill any cells that are, having a problem. So this is why we don't just pour hydrogen peroxide in every single thing that happens, because it can damage your cells. So a good example of a synthesis reaction that we do for demonstration purposes in the lab is sometimes we'll take sodium and chlorine, and then when they get together, they burn and produces a lot of fire, and that is going to make sodium chloride. And of course, I'm dumb and wrote a 2 here. So there you go, sodium chloride. This is a synthesis reaction because we have two things becoming one. Now, on the opposite side of things, when we go dig up aluminum out of the ground, it is aluminum oxide, or otherwise known as alum, and we don't want the aluminum oxide alum for as many things as we want the aluminum for. So we're going to do electrolysis on the aluminum to get the oxygen to float away so that we can do the decomposition of aluminum. So this is synthesis versus decomposition. Now, unfortunately, there are more decompositions than there are synthesis reactions in terms of knowing them for predicting products. So I wanted to just kind of break down decomposition into some other decomposition. So metal plus some sort of anion. A lot of these have unique decompositions. Okay. So the first one we're going to talk about is metal carbonates. So what is a metal carbonate? So we're going to call metal X, and then we're going to call carbonate what it is, carbonate, CO3. So metal carbonates decompose into metal oxides and carbon dioxide. So a great example of this is calcium carbonate, which is chalk. It's made by all creatures that make bones or shells. If you get it hot enough, it will decompose into calcium oxide and CO2. This reverse reaction, the reverse of this decomposition is what, things are doing in the ocean when they're trying to remake their shells. And so that's why there's a nice, very delicate balance between the amount of coral and mollusks and the amount of carbon dioxide. And so the increase in carbon dioxide in the water causes this reaction to try and get mixed up, and the CO2 can kill the reefs and the clams and things like that. And then we have what are called metal hydroxides. So this is going to be X plus hydroxide, which is a minus ion. So then we have XOH is going to decompose into XO and water. So a good example of this is, say we had some barium hydroxide. Well, the barium hydroxide is going to decompose into barium oxide and water. And then we have rocket fuel, so metal chlorates. Metal is our X, and our chlorate is ClO3. This also works with perchlorates, but it's the same thing. It has a -1 charge. So we have XClO3. If we heat that up, it becomes XCl and O2. So a great example of this is potassium chlorate will decompose into potassium chloride and oxygen. The reason why this is rocket fuel is that we've now made liquid oxygen that's hot, and hot liquid oxygen will just react with any fuel you give it. Now, this isn't used in rockets that go out into outer space because we have a bunch of mass being left inside the rocket, and that needs to be picked up by the rocket and taken into space, so it's wasteful. So we tend to do synthesis reactions when we talk about rockets, like the hydrogen-oxygen synthesis reaction. All that water gets blown out the back of the rocket, and so there's nothing left inside the tanks, and so it's a lot better for the rocket. So these are our different metal decompositions, and then we also have acid decomposition. So acids are H plus some sort of anion. Well, in this case, we're talking about what's called oxyacids, which is this is going to be a polyatomic anion. So we have H plus some polyatomic, and what this is going to turn into is going to be the water is going to be taken out of the polyatomic. So we'll say X, and then we'll say like O, some number. And what will happen is we'll have left with XO and then water. So here's a good example of that. This is actually how we make sulfuric acid. We do the reverse of this decomposition. We take the sulfuric acid and its decomposition products will be sulfur trioxide or sulfur dioxide and water. So if we take some sulfur trioxide and water and we put them together either using fire or electricity, it will form sulfuric acid. But you can also heat up the sulfuric acid and it will decompose back into the sulfur trioxide and the water molecules. So those are special kinds of decompositions. So basically, when it comes to synthesis and decomposition, do you have one product? That's a synthesis. And do you have one reactant? That's a decomposition. So finally, we have single and double replacement. So single replacement is some element is going to react with some compound, and then that element, whether it's an anion or cation on the other side, is going to replace it. So in the case of what we say cation replacement, say A is normally a cation, it's going to want to hang out with C, so we'll get AC, and then B will be turned back into an element. You can also have anion replacement. Say A normally likes being an anion, so then the A is going to want to hang out with the B, and we're going to get BA, and then we're going to be left with some C. So let me show you some examples of this. So say, for instance, we took some zinc and some silver nitrate. Well, zinc is normally a positive ion and silver is normally a positive ion. So the zinc is going to want to steal the nitrate. So what we'll get is zinc nitrate, and we'll get aluminum metal. Now, when it comes to single replacement reactions, we actually need to look at what's called the activity series. Basically, if you're going to try and force an element that's already lost or gained its electrons, you're going to need to be more active. You're going to need to be able to force those electrons back onto the thing that lost them or take them away from the thing that gained them. So this here is the activity series of metals. And basically, the higher you are, the more you're able to take away the electrons or give the electrons back to the atom that we're talking about. So in the reaction we just did, oh my God, why does it do that? In the reaction we just did, we looked at zinc attacking a silver compound. And you'll notice that zinc is higher than silver on the activity series. So zinc can replace silver. But say, for instance, we did some lead reacting with some aluminum chloride. Well, we'll have to look at our activity series, and I'll put this on the module, and we have to look for lead and aluminum. Well, there's a lead and there's aluminum. Lead is our element that's going to try and replace aluminum, but lead is not as strong as aluminum. So lead cannot replace the aluminum, and so nothing happens. The same thing happens for anions. And the only anions that it matters for, the activity series for anions, is basically the halogens. Fluorine is the most active. So fluorine can replace anything below it. Chlorine can replace anything below it, and bromine can replace anything below it. So if we took some chlorine gas and we reacted it with some sodium bromide, then the chlorine can replace the bromine. But say, for instance, we took that same chlorine gas and tried to react it with sodium fluoride, well, nothing will happen. Because these guys will replace the things below them. And again, I'll put the activity series on the thing. But you can also, if you're working on this and you don't want to, print something out or have it, you can just type in activity series. And there's a billion activity series charts that show up on here. This one is from either your textbook or one of the other ones that they basically take from each other. Here's another good one. And then sometimes you'll have one that has, this one was very popular with my students when I asked them to make me a poster of the activity series. They all kind of made this one and put it up on the wall. Here's a good one that has, it's basically the same one I posted before, but it has the activity series of the anions as well. And it includes sulfur and phosphorus, and then it puts oxygen in there. But I tend to only ask you halogen ones. So that one's also another good one for you guys to have. So single replacement reactions are difficult because you do have to look on the activity series to make sure that something happens or not. But if not, then all you do is switch their partners. The cation will take the anion, and the anion will take the cation. Double replacement reactions, though, we're not going to worry about whether or not they work. Your book in 11.3 will start getting into reactions in ions, and we're going to ignore that. We're just going to assume that all double replacement reactions take place. Double replacement has the skeleton AB plus CD. What's going to happen is our two ionic compounds are going to switch partners. And so we're going to get AD and we'll get CB. Now, the book will talk about that you really don't know if these reactions are taking place if you don't see anything happening. And here's a great example of that. The acid-base reaction of sodium hydroxide and hydrochloric acid. The hydrogen is going to hang out with the hydroxide, the sodium is going to hang out with the chlorine, and we're going to get sodium chloride and water. This is why acid-base reactions are called neutralizations, is because salt water should be neutral. And, well, base is not, and acid is not. But notice that what we had was a swap of the cations with the anions of the other thing. Now, the reason why your book will say sometimes these reactions don't occur or we don't know if they occur is because this is a clear liquid and this is a clear liquid and it produces a clear liquid. There aren't any bubbles, and the only reason why you would know this reaction took place at all is because that this thing got a little bit hot, depending on how concentrated these two reactions were. But if these things were low concentrations, you might not know that this took place at all. So normally what we're looking for in double replacement reactions is we're looking for what's called a precipitate. So a great example of this is lead. So say for instance we had some lead nitrate, and we reacted it with some potassium iodide. Now in a double replacement reaction, the potassium is going to hang out with the nitrate and the lead is going to hang out with the iodine. When it comes to double replacement, if you have an element that has multiple charges, in this case, this is lead 2. On the other side, just leave it as lead 2. Don't make it lead 4 or any of that kind of stuff. Just leave it alone. There are some exceptions where they will switch their oxidation states, but for our purposes, we're going to ignore that. So in this case, what's going to happen is we're going to make some potassium nitrate and we're going to make some lead iodide. Now, the reason why your book says that this reaction is definitely occurring is because this is kind of rusty, clear liquid, and this is just a clear liquid. Well, this is a clear liquid, but this is a bright yellow precipitate. So when you mix these two together, it looks like you're mixing basically two clear liquids together and you're producing a very, very bright yellow compound. It's very clear that a reaction took place. And so the book kind of suggests that we only consider double replacement reactions to have occurred if we can see a precipitate or if a precipitate disappears or what have you. Well, we're going to ignore all that, and we're just going to assume that all double replacement reactions take place and that some of them, as we'll learn in other chapters, are just reversible, and that's why you don't notice if something's happening or not. So that is double replacement reactions. All you got to do is switch their partners. Pretty simple. And that's everything you need to know for chapter 11. Now, I'm available during the day if you need help with any of the questions. I'll put the activity series thing on the module so that you can reference that when you're talking about single replacement reactions. But other than that, it's a pretty quick and easy chapter because most of it you guys already did. All right, questions before we end the recording and then end the stream for the day. Okay, I'm going to end the recording there.